Okay, so hello to the YouTube audience. So since no one has joined the session in person yet, so I guess I'll wait for 5-10 minutes before we get started so that a few people can join the session in person also. So I guess we'll get started in like 5 to 10 minutes. Okay, so hi Rasika. So we are just getting started now. So yeah, I guess just to reintroduce myself for all the YouTube audience. So hello everyone. I'm Lakshya Saggi, the problem solving TA for the competitive programming uh, NPTEL sessions, the Tuesday sessions basically. And this would be our last session for this semester, like the 12th session. And in this session, we'll again be talking about problems related to dynamic programming. So in this week, we'll cover some more concepts and some further types of problems which you may encounter in dynamic programming. So yeah, and just to remind everyone, so this will be the last problem solving session for us for this semester. But I believe you guys would have already received the notification. But just to remind you guys about that, so there is a summary session also scheduled for tomorrow. Like tomorrow is 17th April, Wednesday, 5 to 6 p.m. So in that session, I'll be basically giving you a brief summary the of the whole course. So basically, how far you have come in the whole course, like starting from week 1 to week 12, I'll be giving a short summary of the whole course in the 60 minutes tomorrow. So hopefully, I'll see you guys there also. And yeah, I guess for now we can focus on the content of today's session, the dynamic programming one. So I guess I'll just share my screen and we can get started. So let me just share my screen, guys. Okay, so I hope my screen is visible to my screen is visible. If it is not, like always, you can inform me via chat and or like if you have any doubts, also you can ask me via chat and I'll try to answer those doubts. Otherwise, I'll just assume that everything is going around smoothly. So yeah. So today we don't have a lot of questions, but I believe the three question like basically today I have prepared like three sets of different dynamic programming problems. So one of these is from the ungraded assignment which you guys had, and one is I have taken from Geeks for Geeks, and one is and there is another problem. So these three, so there are just three problems, but I believe these three cover different types of dynamic programming techniques. So that's why I thought maybe we should be talking about these problems also. So yeah. So these cover different techniques than the ones maybe which we have already discussed or something. So, and these are also some famous problems related to dynamic problems. So you may encounter these in the future also whenever you are giving some exam which has dynamic programming in it or something. So yeah, I guess we can get started then. So this first passage is common data for the questions 1 to 4. So questions 1 to 4 are based on this passage and the figure. So a maze MZ of m rows and n columns is constructed as a grid. So m rows and n columns is constructed. There are some hurdles in the grid which one cannot pass through but can be jumped if there is only one hurdle. One has to start from 0, comma 0 and end in m minus 1, comma n minus 1. So effectively one has to start from this top left corner and reach this bottom right corner. As you can see in the figure in this diagram, this is 0, comma 0 and this is m minus 1, comma n minus 1. And these x's which have been placed are the hurdles in this grid or in this maze. So what we can do is we cannot pass through the hurdles, but we can jump through these hurdles if there is only one hurdle present. So now SP is the two-dimensional table that stores the shortest path to reach the cell ij in SPIJ. So SP is effectively what we are storing as like for the table which we will be using for memoizing in a dynamic programming solution. And it stores the shortest path to reach the cells I, comma j from 0, comma 0. Suppose we want to reach a cell I, comma j, this cell from 0, comma 0. So SPI, comma j will store the shortest path length, which will be used for the same. So the task is to find the least number of steps required to reach the end from start, given that jumping over one hurdle is considered as one step. So what we effectively want is a uh, so we are not interested in actually finding the shortest path because as you can see, like going from 0, 0 to m minus 1, n minus 1, we can only move, suppose we can only move in right direction and in downward direction. So we'll also be using, so maybe I should just write it. Move only in right and downward directions in the grid. So either I can go right or I can go down in this grid. So and in one at one point of time I can just go right. In second step maybe I can go down, then again right or down or something. So it can be seen that the distance between 0, 0 and m minus 1, n minus 1 will always be the same because you will have to take uh something like n minus 1 rights and m minus 1 downs to always go to this coordinate. But so we don't want to minimize the distance, but rather what we want to minimize is the uh, number of jumps which we have to make, number of jumps over the hurdles which we have to make. So the task is to find the least number of steps required to reach, given that one hurdle is considered as uh, one step. So through these hurdles, what we want is we want to go through these hurdles, and we also know that we cannot pass through the hurdles, but they can be jumped from if there is only one hurdle present. So suppose from 0, 0, I can go to the point 0, 2 by jumping over this hurdle x I placed at 1, 0. But note that I cannot go from 0, 2 to something like this coordinate, like uh, 3, 2, because there are two hurdles placed here. And at one point of time, we are only allowed to jump through one hurdle at a time. So going from this point to this point is not allowed, but like going from this point to this point is allowed. Similarly, going from this to this is allowed, this to this to this, and so on. So now we have to sort of minimize the number of jumps which will be needed to reach from 0, 0 to m minus 1, n minus 1. So I hope the question is clear. Then maybe, or maybe this paragraph is clear. Then if we know this, then maybe we can move on to the questions. So first question just states, what will be the appropriate boundary conditions for this SP variable? So SP just stores uh, the shortest path to reach the cell I, j. So SPI, j just stores the shortest path to reach the cell I, j, where shortest path means the path consisting of least number of jumps over the hurdles. So, Rasika, what do you think? So, what should be the value of SP 0, 0? So, would you like to try it out, Rasika? So we are starting at 0, 0, and SP 0, 0 denotes the shortest path to reach the cell 0, 0. So what will be the length of the shortest path if we need to go from 0, 0 to 0, 0? 0, exactly. So Rasika is correct. So the one condition we already know that SP 0, 0 will be equal to 0. That yeah, we just need to, okay, 1 second, guys. Yeah, so SP 0, 0 will definitely be equal to 0. And now we want to select some more conditions, right? So we know SP 0, 0 is 0. And we also want to know like what will be the value of SPI, j. So the option, so second part, we want to find out the value of SPI, j. In all of these options, we want to find out this value. And what will the value of SPI, j? So it will be equal to M if Mij is cross, if Mij is cross. So if the maze has a hurdle at the step I, j, then the problem is asking us what will be the value of sp I comma j. Uh, okay, I think there's some. Okay, so it is already given that we can only move towards right and bottom, so we don't need to mention this. But I think there is some problem in the question. So the question says that there are some hurdles in the grid which one cannot pass through but can be jumped if there is only one hurdle. So these are the hurdles which are given to us. One has to start from this and end in this by moving only towards that's to the shortest path to reach an SPIJ, and that has to be filled. Okay. Okay, so I think this question is a bit is asking something a bit more cleverly. So yeah. So uh the problems so effectively what so if so what we want to find out is the value of SPI comma j when in that I comma j cell we have a cross. So effectively, if there is a hurdle at that step, what this means is that we cannot reach that cell, right? So if mzi comma j has a cross, it means that we cannot reach I comma j. That's I comma j cell. So what this effectively means is that there will be no path going from 0 comma 0 to I comma j cell if that cell has a cross inside it. So I hope my point is clear that so if a cell has a cross inside it, then it means that there won't exist any path from 0 comma 0 to that cross, right? So what this effectively means is that if there exists no path, we can just say that there exists a path of length infinity, right? Because yeah, saying that a path of length infinity exists just means that there does not exist any path anyways. And what we so but the option state the SPI comma j value is m, SPI comma j is n, I comma j is mn, and I comma j is minus mn. And note that we have to select the most appropriate boundary conditions. So even though one boundary condition could have been like SPI comma j could have been set as infinity, but rather we won't set it as infinity, but we'll set it like something which is very high. And if it is very high, like so that for all practical purposes, we can treat it as infinity. So let's look at this entry mn. So we know in this grid that the distance between 0 comma 0 and m minus 1 comma n minus 1 cell is a maximum of m minus 1 plus n minus 1 and not more than that, because we'll need to take m minus 1 rights and n minus 1 rights and m minus 1 downs, and only after that we can reach from 0 comma 0 to this cell. So what effectively does this mean is that uh, this is the maximum number of jumps which will be needed also over the crosses. So effectively, uh, there cannot be a distance of mn between any two. So for any cell from 0 comma 0 to that cell I comma j, there cannot be a distance of mn. So m times n will be larger than the maximum distance which is possible in the grid, which is m plus n minus 2. So the maximum possible distance is m plus n minus 2, and we know that mn is greater than m plus n, right? So what this means is that this distance will always be greater than all the distance entries in this table, all the SPIJ entries in this table for the non-cross, for the non-crossed cells. So what this effectively means is that instead of setting SPI comma j to infinity for the cross cells, we can just set it as mn also, because in this case, Mn and infinity are equivalent because the maximum distance in this table is anyways m plus n, order of m plus n, and Mn is always greater. So setting it as Mn is also sufficient for us. So note that that's why we were asked most appropriate boundary conditions. Setting it as infinity would also have been correct, but in these options, like setting it as Mn also makes a lot of sense. So maybe I should write it down. So correct answer should be option C here. And why is this? I also write down. So it can be easily seen that SP0, 0 will always be 0 because shortest path from 0 to 0 is often 0. Now, if MZ I comma J is a cross, so effectively there is a cross at MZ I comma J. This means that there won't exist a path from 0 comma 0 to I comma J. We can think of this as a path of, we can think of this as there exists a path of very high length, very long length, very long length between 0 comma 0 and I comma j. So I hope what I'm trying to say makes a bit of sense. And so effectively a very long length in this table will be a length of Mn. So Mn will be a very long length. And this is because the maximum distance possible in this table is m plus n. Since the maximum distance possible between 2 points of the grid is m plus n. So effectively like something like m plus n minus 2 actually, because from 0 comma 0 to m minus 1 comma n minus 1, we'll need n minus 1 right turns and m minus 1 downs. So the value Mn is much larger than this. So not, let's just say larger than this maximum distance. So we can set SPI comma J equals to Mn. So effectively we could have set it as infinity also. We could have set it as infinity also. But setting it as Mn works here as Mn is also large for a specific problem. So I hope what I have written and just talked about makes a bit of sense. That since Mn is very large as compared to m plus n minus 2, we can, instead of setting it as infinity, we can set it as Mn. SPI comma j can be set as Mn. Okay, so we have the boundary conditions with us. And now the second problem, maybe I should just shift it. So the second statement effectively asks us, so now the second question just gives us some inductive structures for this problem. Like what will be the values for the table SPI comma 0, SP0 comma Z, SPI comma J. And now we have to mark the incorrect inductive structures from the structures given. Effectively, we are trying to do dynamic programming. So we first need to find out the inductive structure in the problem. So in the first question, we identified the base cases. And after the base cases, we'll need to find out the inductive structures. So, okay. So, uh, let's think of this together, guys. So the first inductive structure says that, so we are setting the value of SPI comma 0 first of all, right? So SPI comma 0 effectively states that the length of the shortest path, if we want to go from let's say 0 comma 0 to something like an I comma 0. So we want to go down to this point, I comma 0. So uh, the only way, what I claim is the only way in which I can come down here is if I'm coming straight down, like, because as soon as I take a right, I'll be in the first column and I cannot come back to the 0th column again because I can only move right or bottom. So I'll have to come straight down to reach I comma 0. And while reaching I comma 0, I'll have to come straight down. But one issue is that let's just consider this point. Let's just consider this 2 comma 0. Suppose I had to reach this 2 comma 0. Uh, if there was a cross just before it, then I needed to effectively hop about this cross. So if I want to reach 2 comma 0, I'll have to take a hop from 0 comma 0 to 2 comma 0. So that will count as a path of length 1. But suppose there was this 3 comma 0 just below 2 comma 0, then for reaching this 3 comma 0, I won't need a hop because there is no this is because there is no cross between 2 comma 0 and 3 comma 0. So effectively, the shortest distance at I comma 0 depends on basically whether there exists a hop before I or whether there does not exist a hop before I. Whether there exists an obstacle before I, a cross effectively, or there does not exist a cross. So if there exists a cross, suppose there exist two crosses together, then this means that I cannot be reachable because we cannot hop along two crosses which are together across. But if there is just one cross before I, so if I minus 1 comma 0 contained one cross and here there was no cross, then I could have just added one hop and I could have just hopped along this cross and I would have reached I. If there were two crosses here, then I could not have reached. And if there was no cross here at I minus 1, then I could have reached straight without adding any more. So this is what we'll be doing in this case also. So we'll have to check that the that for SPI comma 0, the cross if there is a cross before I, then we'll need to hop about this cross. And if there is not a cross, then maybe we'll be okay. So the first claim says that SPI comma 0 will be equal to 1 plus SPI minus 1 comma 0 if MZI comma 0 MZI minus 1 comma 0 is not a cross. So the first inductive structure effectively claims that the shortest path to I comma 0 is 1 plus the shortest path till I minus 1 comma 0 if MZI comma 0 MZI minus 1 comma 0 is not a cross. So if both the entries are not across, I comma 0 is not across, I minus 1 comma 0 is not across, then do we need to add 1? So Rasika, do you think that this claim 1 is correct or this inductive structure 1 is correct or incorrect? So what this claims is there is no, so I minus 1 comma 0 does not have a cross in it. So I can just directly go from I minus 1 to I without any hops needed. And we need to count the number of hops which we need to take. So do we need to add 1 to this SPI minus 1 comma 0? Okay, so Rasika, you are saying that the number of Rasika is saying if we move from I minus 1 to I, then the number of steps will be 1. But note that, Asika, we are not interested in the exact number of steps, but we are interested in this thing, that jumping over one hurdle is considered as one step. And there is no hurdle at I minus 1. So we don't need to jump. So we just need to count the number of jumps. We don't need to count the number of steps. We need to count the number of jumps. And note that I minus 1 does not have a hurdle, so we don't need to jump anyways. So actually, we won't need to jump from I minus 1 to I. We can just straight up move. So SPI comma 0 should be equal to SPI minus 1 comma 0, because we are given that there is no hurdle at I minus 1. If there was a hurdle, then we would have needed to jump, and then we would have added a 1, which is what happens in the second inductive case, that it is equal to 1 plus SPI minus 2 comma 0. If we don't have, okay, so second inductive case is also not written properly, but this is because so we will need to add 1 to the path from I minus 2 to 0, because if I minus 1 has a hurdle, then we need to jump across it. So first we reach I minus 2, then we jump across I minus 1 to reach ith. And this is what the problem is asking us. Okay, so maybe I should just write down all the inductive structures properly. So one should be written as a SPI comma 0 is equal to SPI minus 1 comma 0 if MZI comma 0 comma MZ I minus 1 comma 0 is not equal to cross. So not I'll be representing not equals to by this symbol, the exclamation equal to symbol. So this is what the first structure should look like. Similarly, the second inductive structure, although it is correct, but maybe I should write it again. Like it has some constraints written incorrectly. So second inductive structure claims that if there is a hurdle at I minus 1, then we'll need to hop across that hurdle. If there is no hurdle, then we'll just set it equal to the previous, because no hops involved. No hopping hurdle involved. Okay. And this will be equal to 1 plus SP of I minus 2 comma 0. And this is because, so we know that I does not have a hurdle, because if I already had, then you won't be dealing with it. But I minus 1 has a hurdle. Yeah. So hop over the I minus 1 is hurdle. So something like this. So this is the second inductive structure. So now similarly, we'll move to the third one. So third is again going to SP0 comma j. So it will be similar. So we want to go from 0 comma 0 to 0 comma j now. So this will again be similar to the ith one. So effectively, we'll need a hop if there is no hurdle. So if there is an hurdle, then we'll need a hop. If there is no hurdle, then we won't need an hop. So just so again, this third inductive structure is incorrect, because actually we won't need a hop if we won't need to hop if there is no hurdle at j minus 1, right? Like we only hop over hurdles. Otherwise, we just can't take a step, and we need to count the number of hops. So we won't hop in this case if j minus 1 does not have a hurdle. So maybe I can just correct this. So maybe I should just change the question. Correct the inductive structures. Maybe I should rephrase the question. The given inductive structures have some mistakes in them. So correct these inductive structures. So yeah, I rephrase the problem a bit. So now the third inductive structure again will look something like this, that SP of 0 comma j should just be equal to SP of 0 comma j minus 1 if there is no hurdle involved. So if 0 comma j and 0 comma j minus 1 both don't have a hurdle. Similarly, if one of these has a hurdle, if the j minus 1 has a hurdle, then we'll effectively need a hop. So sp0 comma j will be equal to 1 plus sp j minus 2. If this is not a the 0 comma j itself does not have a hurdle, because obviously we'll be reaching these points, but the j minus 1 has a hurdle. In this case, we'll need to hop over the j minus 1 hurdle. So something like this. So I hope it makes a bit of sense. Then we move on to some more interesting cases, like for a general cell I comma j. Now we move on to some general I comma j where let's assume like I is greater than 0 and j is greater than 0. So for a general I comma j, how do we update the values? So what we can essentially say is okay, there are some hurdles which cannot but can be jumped if there is only one hurdle. SP, that's the shortest path to reach, is find the least number of steps required to reach the end from start, given that jumping over one hurdle is okay. Maybe the question also needs to be rephrased a bit. That shows the shortest path. The task is to find the least number of steps required, given that jumping over hurdle is considered as one step. So just mentioning that, note that so I just want to make this clear in the question itself that we want to count just the number of jumps and not the that shows the path with least number of jumps to reach the cell I comma j. The task is to find the least number of jumps required to reach from end the end from start. So yeah, I hope the question makes a bit more sense now. Like yeah. So what I've done is like just make the question a bit more explicit that we are just counting the number of jumps and not the steps. So we need to like going from 2 comma 0 to like something like a 3 comma 0 will be counted as 0 jumps because there was no hurdle. Similarly, going from 0 comma 0 to 2 comma 0 will be counted as one jump because we need to jump like this, right? Okay, so yeah, I guess this the question makes a lot more sense now. Otherwise, previously the language was a bit confusing. So now again in this fifth inductive structure, so what it's saying is the shortest path from I to j is equal to 1 plus minimum of I minus 1 to j minus 1 if I comma j, I minus 1 j and I comma j minus 1 all do not have a hurdle. So effectively, maybe before looking at this like this, just look at a general cell I comma j. So how can we reach this cell I comma j? So there are only two cases, either we reach it from the right or we reach it from above this cell. I comma j can be reached only in two ways, either from above or from right. And now what the problem actually asks us is to find the minimum number of hops in which we can reach here, right? So suppose I consider the last step to be the one where I come from above. And so what there are two possible cases if I'm coming from above. If I'm coming from above, then there are two possible cases. Either the I minus 1 comma jth entry was a cross. Then actually I would have hopped from directly from I minus 2 to I. So I would have added 1 to this entry of I minus 2j. Similarly, the second thing may be that there is a maybe I'm coming from the right. And if I'm coming from the right, then this means that there might be a cross here or there might not be a cross here. So if there is a cross, then I'll need to jump from I minus 2 to I. And if there is not a cross, then I can just straightforward go from I minus 1 to j minus 1 to j, something like this. So I hope this sort of makes sense. So effectively, we'll need something like four cases, like either both of these. So one case will be if both of these have a cross, then we'll need to take the minimum of 1 plus this. So 1 plus the number of jumps required to reach this point, and 1 plus number of jumps required to reach this point. And second case might be there might be a cross here, there might not be a cross here. Then we need to directly go from here to here or from here to here. So I hope this sort of argument makes sense. Maybe I should just delete these and just write the question as write the inductive structures for the given problem. Something like this. Because all these inductive structures sort of have mistakes, so there is no point in just saying that correct these. So now what we have to do is effectively SP. Okay, maybe I can. Maybe we can just leave it as it is. So SP I comma j will be effectively minimum of uh, SP I minus 1 comma j. Either I can come from the right or I can come from above. SP I comma j minus 1. And this will be if both these cells I minus 1j and I comma j minus 1, both of these do not have a cross. Because if they had a cross, then we sort of know that we can't go from these cells. We'll need one hop. So right now we don't need one hop because these cells don't have a cross. So what this means is that minimum of SPI minus 1 comma j, SP, and this can only, and this is when if obviously I comma j should not have a cross. I comma j, I minus 1 comma j, and I comma j minus 1. all of these don't have a cross, then we can set it to something like this. Now, similarly, if some of these have a cross, some of these don't have a cross, then we need to obtain this. So the second case can be, maybe these two don't have a cross. Like, let's say I comma j does not have a cross, that we know, but I minus 1 comma j also does not have a cross. So effectively, the cell which is just to the left does not have a cross, but the cell which is just above has a cross. So what this means is that we'll need a hop if we are coming from above. We won't need a hop if we are coming from the right, if we are coming from the left, because this is not equal to a cross, but we'll need a hop if we are coming from above. So what this means is that we won't need a hop if we are coming from the left. So this will remain as it is. But if we are coming from above, then we'll need a hop. And actually, we'll be hopping from the j minus 2 itself because we'll be skipping the j minus 1 itself. So this entry will be something like this. Now, similarly, another scenario can be, so this can be a bit confusing, all of these statements, but just trust me, if you guys try to do it yourself also, you'll be able to do this once you get the high level idea. Just keep this picture in mind. So yeah, the second case can be, okay, so here we assume that left side is free and the upward side has a cross. Similarly, what can happen is maybe left side has a cross and upward side is free actually. So left side has a cross, but upward side doesn't have a cross. So in this case, what we'll do is, so we'll need to hop if we are coming from the left. So this term indicates we are coming from the left. So we'll add 1 to this. And if we are coming from above, will come as it is. And note that here will be j minus 1 because we are not hopping. And here it will be I minus 2 because we are indeed hopping. So something like this. And note that we are taking always the minimum of these two entries because we want to take the minimum possible hops, right? So from both these two roots, we want to take the root of minimum possible hops, something like this. And now the last condition will be, so what we have considered is both above and left don't have a cross. Left has a cross, above doesn't have a cross. Left has a, above has a cross, but left doesn't have a cross. So we have considered these three cases. The only remaining case is that when both of these have a cross. The left and above, both of these have a cross. Then what will we do? Then actually, if both of these have a cross, and obviously mzij does not have a cross, I comma jth is not a cross element. So if both of these have a cross, the left and above side, so we'll need to effectively take a hop whenever we are coming from any direction. So we'll need to take a hop if we are coming from the left. Similarly, we'll also need to take a hop if we are coming from the right and take the minimum of that. Okay, so these will be the inductive constraints for us. And I hope I've covered all of these. Like, yeah, so like we have covered all the cases because either we can be in 0th row or 0th column or in a general I comma j. And we have covered all the cases like whenever the above and both have a cross, when just above has a cross, when just left has a cross, and when both don't have a cross. So yeah. So I hope these constraints are clear to everyone. So if there's any doubt, like you can ask me via chat, I'll try to explain it again. So the language of the question might have become a bit confusing and you may have felt lost. So you can ask me again, I'll try to explain this again if you feel. Otherwise, I'll just move on to the third question. Okay, so we have constructed these inductive cases, right? Like we have constructed these inductive cases and we sort of know that what to do in each of these cases. So now the problem asks us to, so suppose we are actually doing a dynamic programming algorithm. So we need to fill this table in some order also. We have the inductive structure on this table SP, but we also need to fill out this table SP, right? So what should be the order in which this table SP gets filled? So uh, any idea, Rasika, in what order should this table SP get filled? Okay, so Rasika is saying C, and she's also saying that A and B also seem correct. So yeah, I think there is a bit of, again, a bit of language confusion in this option, but effectively, first I want to see you. So first I want you to see the diagram picture. So actually, how do we aim to fill up this table? So how are we aiming up filling up this table? So whenever computing the value for some cell I comma j, what we would actually want is to have the values to the left of it and to the above of it. So all the values above this cell and all the values left to this cell, we would need to pre-compute these values. And how can this be done? So either we can fill up the table in this manner, like if we go along this manner, like we suppose fill up the first row, then we fill up the second row, then we fill up the third row. So whenever we are encountering a cell, its previous row would have been filled and the column just left to it would also have been filled. So this is one manner, and similarly another manner can be, suppose we fill up the first column, then we fill up the second column, then as soon as we start filling the third column, for any cell, we know the cell in its previous row has been filled and the previous column has also been filled. So in this case also, in this sort of traversal also, if we fill up the table, it will be okay. So what we can do is either we can move row wise, fill up row wise, row 1, row 2, row 3, or we can fill up column wise. So this is what actually these options A and B are actually saying. So this might seem a bit confusing. So A option is saying left to right, then top to bottom. So what this means is that we'll fill the table from left to right. So we'll fill up the 0th column, first column, then second column, then 0th column, and then last in the last n minus 1 column. And how are we filling these columns? In these columns, we are filling these columns top to bottom, like this first, this second, this third, this fourth, this five, and so on. So this is what this option is saying. Similarly, B option is saying top to bottom, then left to right. So we'll be filling first this top to bottom. So this row, this row, this row, this row. And inside the row, we are filling it up left to right. So whenever we are in the ith row, first we'll be filling up 0th column, then first column, then second column, then third column, and so on. So consider these as for loops. So what this is saying is that the first for loop would be going from left to right, and the second for loop will be going from nested for loop will be going from top to bottom. And similarly, this is saying first for loop is going top to bottom, and the nested for loop will be going from left to right. So yeah. So these options, top left corner to bottom right corner, don't make much sense. Like, how do we even go from top left to bottom right? Like, that does not seem an actual way for going diagonally, right? We can't go diagonally because for a cell we need to have its upward and the leftward values. So the options B and C are A and B are actually correct. Options A, comma B are correct. And why is this? Maybe I can explain this a bit better. Option A says that we'll fill the first column then second column, and so on. Each column gets filled in the in top to bottom manner. So this ordering is correct. So this is why option A is correct. Similarly, for option B actually says that we'll fill the first row, then second row, and so on. And each row gets filled in a left to right manner. Both these orders of filling up are correct. So yeah, that's why options A and B are correct. So these don't make much sense because we can't fill up diagonally. Yeah, so Rasika, you are saying start cell is top left corner and end cell is bottom right corner. So yeah, you are right that start cell is top left and this is bottom right. But what I'm saying is this option does not make that much sense because what it's actually suggesting is maybe start at top left. Like it's not giving us the actual traversal order, right? We know that we have to start at the top left and we have to end at the bottom right. But how do we traverse the cells in between? Like option C and D do not tell us how to traverse the cells in between. It just says like go from top left to bottom right. But the order of traversal is also important, right? Suppose I go to suppose I start from top left, I start from 0, 0. Then I go to this I comma 2. And then I go to some arbitrary another vertex. And then in the end, I just go to the bottom right. But that order will be incorrect because if I just go after 0, 0 to this point I comma 2, I won't be able to obtain its value since I have not pre-computed these two entries, the ones left and above it. That's why this option is sort of useless. Maybe you can ignore this like also like yeah, this option actually does not give us the information or something. So yeah. So maybe like the question was not intended to like ask you which order is correct exactly, but I just wanted to inform you guys that the correct order of filling up this table can be either row wise or can be column wise also. Like let's just ignore these options because they are very vague in language. So okay. So the fourth question says that what are the possibilities when the value at SP m minus 1 comma n minus 1 is greater than m plus n minus 2? So we know that the maximum value, the maximum number of jumps, if we go from 0, 0 to m comma n, can be m plus n minus 2 only, since there are just m plus n minus 2 rights and downs. So what are the possibilities when this value is greater than m plus n minus 2? So suppose what we obtain in the end is that this cell has a value of m greater than m plus n minus 2. So the bottom right cell has a value greater than m plus n minus 2. So that can only be when actually we are not able to reach the cell. Only in that case, the value will be greater, right? Otherwise, there will be if there exists a path, then the number of hops on that path will be less than m plus n minus 2. So the only way in which the value will be greater than m plus n minus 2 will be when the bottom right cell is not reachable from the top left cell. So there will be no way to reach the end without a double jump. And so double jump means that jumping over two hurdles at once. And like this is sort of true because like there will be no way to reach. So suppose there can be a case that if we are allowed to use double jump, then we could have reached, but otherwise we could not reach. That's why it is one of the possibilities. There are two continuous columns of hurdles. So if there are two continuous columns of hurdles, again, we can't go across them because we'll need two. So we can't jump across two continuous columns. Similarly, we can't across jump across two continuous rows because like I hope this is clear. And there is a continuous diagonal hurdles from bottom left to top right. Okay, so this is a bit interesting. So what this option says is that there is a continuous diagonal hurdle from bottom left to top right. So what this means is that suppose there is a diagonal hurdle like this, like bottom left to top right. So something like this, there's a diagonal along which hurdles are present, right? So do you think this kind of diagonal, like which starts at something like m minus 1 comma 0 and goes along this direction, will, because of this, will we be stopping? So Rasika, do you think like will this sort of diagonal stop our path, or we can jump across this diagonal? Like the diagonal which goes from starts from this bottom left and goes like this in the top right direction. Yeah, so Rasika is saying we can jump across this since one jump over the is allowed. So yeah, Rasika, you are correct. Good job. So if this sort of diagonal is present, then we can jump across it. Suppose there was a cross in this cell and I was at this cell, then I could have jumped across this cell. But note that if two continuous columns have crosses, then from this cell I can't go across to this cell because I can't jump across two continuous crosses. So that's why option D is not correct, but option C. So all these three options are correct. Because of these three, uh, so there will be no way. So maybe I should answer. Option B, A, comma, B, comma, C are correct. And why is this? So just this is because SP I minus 1 greater than M minus 2 implies that there does not exist a path from 0, 0 to M minus 1 comma N minus 1. So something like this. Using just single hurdle hops. So something like this. And because of these three options are correct, and this option is wrong. Okay. So this was the fourth question. So now maybe we can move on to the fifth question. So like this whole the first four questions were effectively part of this just one problem statement, right? Now similarly, I have two more problem statements like this prepared. So I believe we'll be able to cover these in time. So the fifth question says that suppose we are given n boxes, and I think this is also present in your ungraded assignment. So this problem is also present in your ungraded assignment, but you guys don't have the solution to it. So I'll help you guys with this. So like yeah, since this is part of ungraded assignment, so this is a quite a nice problem, and I think the tricks involved in this will be useful to you guys in the future also. So there are n boxes numbered from 1 to n. Now we have to distribute k toys among these boxes, and each box from 1 to n must contain between 0 and ai toys. So the ith box will contain AI toys. And this suppose AI is already given to us. So what we mean is the ith box will contain any number of toys between 0 and AI. So if AI is 5, then the ith box can contain 0 toys, 1 toys, 2 toys, 3 toys, 4 toys, or 5 toys. So now every toy must belong to exactly one box. So obviously, since we have toys and like every toy can go into one box only. So now what we need to find is the number of ways in which the toys can be distributed. So what this means is that we have to put the toys in these inside these boxes. We are given k toys. We are given these n boxes, and for each of these boxes, we are given constraints of lying between 0 and AI. And now the problem asks us that every toy must belong to exactly one box. Find the number of ways in which the toys can be distributed. Here, two ways are said to be different when there exists a box that has different number of toys. So what the problem is asking us is that, okay, so two ways. So effectively, we just have to fill up all of these boxes from 1 to n. And these boxes are said to be different when there exists a box that has different number of toys. And now we want to suggest an efficient algorithm for the problem. So what we actually want to do is find the number of ways in which the toys can be distributed inside the boxes. So I hope the problem statement is clear. Like maybe this sort of thing you don't need, but okay, nevertheless. So we are just given these k toys and we are given these values a0, a1 till a1, a2 till an, the maximum number of toys which can fit inside the ith box. And now every toy must belong to exactly one box. Now we need to find out the number of ways in which the toys can be distributed inside the boxes. So suppose these k toys have to be put inside these n boxes. And now we have to find out the number of ways in which these toys can actually be put inside the boxes. So what would be an efficient algorithm for the problem? This is what we are asking. And obviously, since this is dynamic programming, since right now we are talking about dynamic programming session, so most probably this can be solved using dynamic programming. So any ideas, Rasika, if you have done the ungraded assignment or something? Maybe I'll give you like 5 minutes to think about it. So maybe you can think about it for 5 minutes and then maybe I'll try to answer this. Since this is a question from the ungraded assignment, so I believe you guys might also have some idea about it. If you don't, like, just try it out for 5 minutes, and after that, I'll answer this for you. So I'm muting myself for 5 minutes. Maybe you can think about it till Okay, so another thing to note is that just assume that this AI is not very large for all I. So like something like a complexity of n times the max of this AI is okay with us. Okay, I guess we can discuss this. So like let's just consider something like a DPI comma J. Maybe I'll just discuss it myself since there were no answers in chat. So yeah. So just consider the value like something like a Tij. maybe. And what does this value Tij store? So it stores the number of ways in which J toys, suppose we did not have K toys, but we only had J toys, can be distributed in the first I boxes. So we are given these N boxes. Suppose we take the first I boxes out of these. So Tij just represents if we just consider these I boxes and if we wish to place uh, J toys inside them, then what are the possible number of ways in which we can do so? So I hope the problem statement is clear. So note that still all of these constraints are active that for each box I, there must be between 0 and AI toys inside that box I. So this is sort of what we are claiming, but we'll only be considering the first I boxes for this term Tij. And only after that we'll consider for others. So now I hope you can write the base case yourself. So base case will be something like a try it yourself because it won't be too difficult. Try it yourself. I'll just leave this as an exercise for you guys. And now the inductive step will be, so suppose I wish to compute something like this Ti comma j, right? The number of ways in which j toys can be distributed in the first I boxes. Suppose I am given I boxes and I want to see like the number of ways in which I can distribute actually j toys. So what can happen is let's consider the ith box. So let's consider the ith box which I'm talking about. So there are n. So there are like let's consider something like 1, 2, 3, 4, 5 till I minus 1th box and the ith box. So these are boxes, not the numbers in sorry, not the number of toys inside them. So this ith box can have 0 toys, or it can have 1 toy inside it, or it can have 2 toys, or 3 toys, or 4 toys, or 5 toys, till AI toys. So this ith box can have uh, 0 toy inside it, 1 toy inside it. So there are AI plus 1 number of ways in which we can place the toys in this box. Either there will be AI toys, there will be AI minus 1 toys, AI minus 2 toys, till 0 toys. And obviously we'll have to so basically, if j is less than ai, then there can be maximum of only j toys. So, but yeah, that's what I'm trying to say. So the ith box, if ith box has sort of only 2 toys inside it, then the problem reduces and we have to place total number of toys as j. Then the remaining I minus 1 toys, then the remaining I minus 1 boxes will have to have something like j minus 2 toys. Similarly, if ith box only has one toy, then these first I minus 1 boxes will have j minus 1 toys. If ith box has 0 toys, then these boxes will have j toys. Similarly, if this has 3 toys, this will have j minus 3 toys, and so on. And since all of these are disjoint cases, we'll need to sum them. So this will be something like ti comma j minus 1, or maybe just like, ti minus 1 comma j, because this is the case when ith box has 0 toys. So the remaining I minus 1 should have j toys, plus t of I minus 2, sorry, I minus 1 comma j minus 1, plus t of I minus 2, sorry, I minus 1 comma j minus 2. So we'll be summing these up till t of I minus 1 comma j minus ai, because ith box can have a maximum of ai toys. So it will be something like this. So note that if j minus ai is negative, then we'll be only summing these up till this index reaches 0. Maybe I should write this. If j minus ai is less than 0, then sum only till because we don't show negative coefficients, right? Ti minus 1 comma 0. So maybe I should also write the reasoning behind it. So I have already discussed this, but still just write this. The ith box can have 0 toys, 1 toy, 2 toys, till I toys. So we'll need to fit the remaining toys inside the first I minus 1 boxes. Since all these cases are disjoint, total number of ways will be sum of these individual cases. So this is the reasoning, and from this we obtain something like this, that ti comma j will be nothing but ti minus 1 comma j plus ti minus 1 comma j minus 1, and so on. So this is the inductive step which will be needed. So in this manner, like, it's not too difficult to see that this algorithm will take something like, and so there will be something like I will be equal, so I can go from 0 to capital N. So like I can go from 1 to capital N because there are n boxes in total, and J can go from something like 0 to capital K because we are distributing K toys. And for computing one of these entries, we'll be taking something like an AI amount of time, because this will be sum of AI entries. So total time taken will be something like n times k times AI. So the maximum of all the AIs. So, and we know that if AI is, so yeah, so something like this. So I hope uh, you get the idea that the complexity will be something like, I'm not writing down the complexity, you guys can easily see this yourself also. Or maybe I can give it a try to yourself also. So there are n boxes, k toys, and in each iteration, we are taking some of small AI different entries. So yeah, that's why its complexity will be something like NKAI. So time complexity priority of self. So I've given already the hint, but yeah, just do it yourself. So yeah, and this is sort of the algorithm which we'll be using to find out the values. So now just to see this, let's compute the answer to the input given below. Suppose n is 3 and k is 4. The AIs are 1, 2, 3. So this is also in your ungraded assignment. So what do you give? So AI, so basically this means that A1 is 1, A2 is 2, A3 is 3. So let's just write this algorithm, implement this algorithm. So so we are given that n is 3, k is 4, AIs are this. So let's just find out the value of T. So there are three boxes. So this will be something like, so if we have T1 comma 0, so this will be something like a base case. So suppose we only have first box. So the first I boxes, so we only have the first box and we need to create a sum of, and we need to distribute 0 toys. In how many ways can it be done? It can only be done in one way if the first box has 0 toys. Similarly, T of 1 comma 1 will also be 1 because first box can only have one toy. Or yeah, but note that T of 1 comma 2. So what this means is that we only have first box and we need to fit in two toys. But note, so I'm writing out these base cases only. These are only base cases because at one toy we can't go to I minus 1th, right? Because then there will be 0. So if there is one box and there are two toys, then we can't fit into these two toys into the first box because first box only has a capacity of 1. So there will be 0 ways to fit in these toys. And similarly, T1 comma 3 will also be 0. And similarly, T1 comma 4 will also be 0. So I'm taking till 4 because we total have k equal to 4 toys. So this is what we will be having as a base case, that T of 1 comma 0 and T of 1 comma 1 is 1 and the remaining are 0 because the first box can only fit in one at a time. Okay, and now it's easy to find out T of 2 comma 0. So T of 2 comma 0 will be nothing but T of 1 comma 0 plus T of 1 comma minus 1 and so on. So it will just be a 1 here. Similarly, T of 2 comma 1 will be equal to T of 1 comma 1 plus T of 1 comma 0. So it will be T of 1 comma 1 plus T of 1 comma 0. So it will be 1 plus 1, which is 2. Then T of 2 comma 2. So I hope you are following along. I'm just, for now, for calculating these, I'm just following this recursive relation. So T of 2 comma 2 will be again, so inside the second box, we can fit as many as two toys. So it will be something like T of 1 comma 2 plus T of 1 comma 1 plus T of 1 comma 0. So which will again be a 2. Now for T of 2 comma 3. So for T of 2 comma 3, so we can fit in maximum of two toys here. So if we fit in 0 toys, then it will be something like 0, then 0, and then this will be 1. And we'll only sum till T of 1 comma 1 because uh, J is 3, but AI is only maximum 2. So we can't fit 3 toys into the second box. So we won't count this 1 comma 0 case. So we'll only be counting till this case. So this will be equal to 1. Similarly, T of 2 comma 4 will be equal to T of 1 comma 4 till 1 of 3 till sum will go to 1 comma 2 because we can fit maximum of 2 toys. So this will be just some of these three terms which will be 0. And now we come to third box, which is what we finally want. So T of 3 comma 0 will be equal to 1 because T of 3 comma 0 will just be equal to T of 2 comma 0, which is 1. Now T of 3 comma 1 will be equal to T of 2 comma 1 plus T of 2 comma 0, which will be 2 plus 1, which is 3. Similarly, T of 3 comma 2 will be equal to t of 2 comma 2 plus t of 2 comma 1 plus t of 2 comma 0, which is 2 plus 2 plus 1, which will be something like 5. And now we also need like a t of 3 comma 3, and 3 comma 3 will be nothing but either we can have 3 2 1 0. So this will be 1, this will be 2, 1 plus 2 plus 2 plus 1, which will be a 6. And similarly t of 3 comma 4, t of 3 comma 4 will be what we actually want. It will be just so this can fit maximum of 3. The third box can fit maximum of 3. So we'll be only taking sum till t of 2 comma 1. Sum of these entries, which will be 1 0 plus 1 plus 2 plus 2, which will be just 5. And note that this is the entry which we want, because what we want is we have n boxes and we want to distribute k toys. So we have 3 boxes and we want to distribute 4 toys. So 4 toys can be distributed in 5 ways, but 3 toys could have been distributed in 6 ways. But this is what we actually want. So even though we increase the toys, the number of ways might decrease in this question. So yeah. Hence, there are t of 3 comma 4, which is equal to 5 ways. Okay. Yeah. Okay, so I hope this sort of calculation is clear to everyone. So if there are any doubts, like you can ask me via chat. Otherwise, I'll be moving on to the last question for the day. And probably the last question for this NPTEL sessions. Okay. Maybe I should not maybe this I can modify this question a bit so that yeah. Okay, so this is the last question for us. So this is again a bit subjective and it has been taken. Like the idea for this question has been taken from Geeks for Geeks. I change this question a bit for the purpose of this course, but yeah, the high level idea of this problem I found from Geeks for Geeks. And this is also a question which you will see in multiple tests. So yeah. So the problem states, so this problem is based on matrix multiplication. Suppose we are given 4 matrices M1, M2, M3, and M4. And these matrices, we have been given that these are dimensions P cross Q, Q cross R cross S, and S cross T respectively. And note that these matrices can be multiplied in several ways with different amount of total scalar multiplications. So for example, if we multiply M1 cross M2 and M3 cross M4, suppose we first calculate this M1 cross M2 and then we calculate this M3 cross M4, and then we take the product of these two products, then the total number of multiplications will be how much? First, we'll have to multiply M1 cross M2. So we'll have to multiply a matrix of P cross Q with a matrix with dimension Q cross R. And this takes something like a P times Q times R time. Like this is something which we already know from high school algebra, that the number of multiplications required. Suppose we are given two matrices A cross B and B cross C, then multiplying those will take something like A into B into C time. So multiplying these two matrices takes PQR time. Similarly, M3 and M4 multiply together. So M3 has R cross S, M4 has S cross T. So this will take RST time. So RST. And note that, so this resultant product of M1 cross M2. So M1 cross M2 is now a matrix of dimensions P cross R, because this Q was common. It's leaved out, and M1 cross M2 has a dimension of P cross R. Similarly, M3 cross M4 has a dimension of this S gets cancelled, so R cross T. So now I have to multiply one matrix of P cross R with matrix of R cross T dimension. So it will take PRT time. So this is PRT. So note that if I multiply the matrices in this order, that M1 cross M2 first, M3 cross M4, and then the products taken together, then I take something like PQR plus RST plus PRT time. So I hope this is clear. This calculation is clear. Similarly, suppose I suggest an alternate way to multiply these matrices, which is to first multiply M1 with M2. So this takes again something like a PQR time. Then this results in a matrix of dimensions P cross R. And now this matrix is multiplied with M3. And note that M3 has dimensions R cross S. So this takes PQR time initially, and then this is a P cross R matrix, and then gets multiplied with R cross S. So this takes PRS time. So this multiplication together will take now PRS time. And now the resultant matrix becomes of dimension P cross S. And when this is multiplied with matrix of dimension S cross T, this will take PST time, which is given here. So I hope the high level problem is clear to everyone. So now what we want to find, so clearly these two are different in quantity, right? PQR plus PRS plus PST might be different from PQR plus RST plus PRT. So these values might be different. So the order in which we multiply the matrices also changes the number of computations which we need to do. So sometime maybe this is smaller, then we would have multiplied the matrices in this order. If this was smaller, we would have multiplied the matrices in this order because we want to minimize the number of multiplications, right? Now the problem asks us to suggest an efficient algorithm to determine the order of multiplication of matrices to minimize the number of total scalar multiplications. So now what we want is an algorithm to determine the order of matrix multiplication to minimize the number of total scalar multiplication. So we want to minimize the number of multiplication. The total scalar multiplications here was something like this. Here was something like this. So now suppose we in the matrices we are given their dimensions. So we are given 4 matrices and their dimensions. And then we want to minimize the number of total scalar multiplications. How do we find an algorithm for this? So I hope the problem is clear. And now maybe I myself will give you guys a high level idea of how to do this. So let's just consider not just this problem, but a very general problem rather. Suppose we had matrices, not just 4 matrices, but we had something like n matrices. So suppose we had M1, M2, M3 till Mn. So suppose I had these n matrices. Right. And I needed to multiply these matrices together. And note that uh, and note that the this matrix. So whenever matrices have to be multiplied, like the number of columns in M1 should be equal to number of rows in M2. Similarly, number of columns in M2 should be equal to number of rows in M3 and so on. So something like this, which happens here, like M1 has P cross Q, then this Q should be common in M1. R should be common in M2, M3. S should be common in M3, M4. Only then can matrices be multiplied. So let us consider the general version of this problem. So I'm doing the general version, and same will apply to the 4 matrices also. I'm just doing this because, yeah, this is easier to explain in my opinion. Something like this. Suppose we have to multiply the matrices M1, M2, M3 till Mn. And we are also given that also assume that dimension of matrix Mi is equals to Ai cross Bi. So what this means is that the matrix Mi has Ai rows and Bi columns. And also like we are given that these matrices are multipliable. Also, assume that we are given that these matrices have dimensions such that their multiplication is feasible. So what do we mean by that? That the number of columns in the first matrix should be equal to number of rows in the second matrix. Similarly, number of columns in this matrix is equal to number of rows in this. So effectively, B1 is equal to A2 and B2 is equal to A3 and so on. So this statement basically implies that. So now we sort of want to find out the, now we need to determine the order of multiplication to minimize the total scalar multiplication. So we need to minimize the number of total scalar multiplications. And how do we multiply the matrices so that this is minimized? Okay. So a very high level idea on how to view this problem is something like this. So we know that whenever, so let's just look at some of these cases here, right? So what happens is in this case, we first multiply M1 with M2. Similarly, with we multiply M3 with M4. And after this, we are left with just two matrices. One matrix is the product of M1 and M2. Second matrix is the product of M3 and M4. And then we multiply these two matrices together. So in the last step, we are just multiplying two matrices. Here also what we are doing is we first multiply M1 with M2, then we multiply this product with M3. And in the end, the product which we are left with, this product, gets multiplied with this matrix. So this is a matrix in its own right, and this gets multiplied with M4. So always in the end, we are sort of multiplying two matrices. So I hope I'm sort of making sense. So what we are sort of doing at the end is we are left with multiplying two matrices. And note that these two matrices will be product of consecutive matrices. Like here, M1, M2, and M3, M4 were multiplied in the end. Here, M1, M2, M3 was multiplied with M4. So whenever we are left with two matrices, they will be like something like products of contiguous matrices. So what I mean to say is, so in the last step, suppose we are multiplying these and we have some order in which we are multiplying. In the last step, what we'll be left with is multiplying M1, M2, M3 till some Mi with the matrix Mi plus 1, Mi plus 2, Mi plus 3 till Mi. So I hope what I just said makes a bit of sense, that in the last step of matrix multiplication, when we are just left with two matrices, the two matrices will be of the form, first will be M1, M2, M3 till Mi, and second will be Mi plus 1, Mi plus 2, Mi plus 3 till Mn. And these two matrices now get multiplied. And yeah, this is sort of uh, the final multiplication which we'll be getting at. So note that if I already have the answer to the minimum number of steps of M1 to Mi and the minimum number of steps from Mi plus 1 to Mn, then I just need to add the steps which I obtain in the end to the final multiplication. So this is a sort of high level idea. And now maybe I can sort of. So this is how you can think about the DP solution for this. And now maybe we can define the multiplication properly. The the DP memorization technique properly. So inductive structure will look something like this. So let's say what we denote by Tij. So Tij actually denotes the uh, let's suppose we just don't need to find out, we don't need to determine the order, but we just need to find out the minimum total scalar multiplication. Like because determining the order is not that hard after we have determined the total scalar multiplications. So yeah, I'll just be talking about the number of total scalar multiplication being minimized, and you can modify it to determine the order yourself first. So let Tij denote the minimum number of scalar multiplications needed to multiply mi, comma mi plus 1 till mj. So what is saying is, suppose I was given I was given some matrices out of this set of matrices, the matrix mi plus 1 till mj, and I was asked to calculate just this product, mi with mi plus 1, mi plus 2, mi plus 3 till mj, and I want to find the minimum number of scalar multiplications. Suppose this was the sub problem which was given to me. I'll define this as Tij. So what I actually want to calculate is T1 comma n, because I want to calculate the product T1, T2, M1, M2, M3 till Mn. I want to calculate this product, right? So what I actually want is T1 comma n. But suppose I am given, suppose I define my subproblem as Tij. And now suppose I want to calculate this Tij. So how do I calculate this? So the idea will be similar to what I just described to you guys. So note that if I'm multiplying this mi with mi plus 1 till mj, what I already know, so what I know is there will exist some I prime here, or maybe there will exist a k here, such that the matrices mi plus 1, mi plus 2 till mk get multiplied at the last step with the matrix mk plus 1 till mj. So in the end, we'll be left with matrices m1, mi plus 1 till mk, and the matrix mk plus 1, mk plus 2 till mj. And we'll be multiplying those two together. So the total number of multiplications in that step will be something like, we'll first be multiplying t, the mi's with k, like the mi to mk matrices. And I'll also be multiplying the mk plus 1 to mj matrices. Mk plus 1 comma j. And then in the end, we'll be multiplying the matrices which we obtained here, the my till mk and then mk plus 1 till mj. And the dimensions for these matrices will be, so mi will have like something like a dimension of ai, and the second term which will be coming is the number of columns of mk, so which will be something like a bk. And then the last term will be number of columns of j, bj. So now that you could have written this as bk, or you could have written it as ak plus 1, and both will be the same. So the this is what we'll be obtaining if we multiply the first k matrices. If we do this multiplication in the last, the matrix, matrices till the kth index, and then k plus 1 at till mjth, and then in the last we multiply these two matrices which we obtain. So this will be the number. And now since we have a choice over all k, so we'll be minimizing it over all k, this term. And by this, we'll be actually able to obtain. So we minimize over all possible k, this value, tik plus tk plus 1j plus ai bk bj. And this will give me the value tij. And maybe I can just write down this. Suppose the last matrix multiplication is between the matrices mi mi plus 1, mi plus 2 till mk, and I'm just giving you guys an intuition of what to think about this. Mk plus 1, okay, maybe I can use this. Mk plus 1, Mk plus 2 till mt. Yeah. Yeah. So suppose the last matrix multiplication is between the matrices this. Then what we are doing is then we can iterate over all k and find the minimum number of steps required, minimum number of scalar multiplications required for Tij. So this is the high level idea, and we can sort of formalize it using this formula. So Tij is minimum over all possible k, the value Ti, comma k plus Tk plus 1, comma j plus Ai pk pj. This is how we can calculate the value Tij. And similarly, you will have to write down some base cases. So base case, you can try it yourself. Base case, again, it's not too difficult to try it yourself. So this is the inductive case. Inductive case is this. And from this, we'll just output the value of t. After calculating this, we'll output the value of t of 1 comma n. And note that how will we fill up this table? So I comma j needs something like I comma k and k plus 1 comma j. So this is also something you need to keep in mind, and you can think about this also yourself. Order of filling up the table. This is also something which I leave it to you, which I leave to you guys, because I don't think it's too difficult. You can think about it. Maybe I can just mention like the order in which you will need to fill up this table will be something like a diagonal order. So something, okay, like a diagonal order. So yeah, this is this is the general version. Suppose so here we are only given 4 matrices. So uh, for 4 matrices, this just goes on. The I and J only become like small between 1 and 4. But for the general problem, this is the algorithm, how you solve this. And this is a very famous problem, and maybe like it will be asked to you guys at some point in the future in your interviews, in some tests, and so on. But yeah, this is how you can sort of solve this problem. Okay, so I hope this is clear to everyone, and if there is any doubts, like you can ask me via chat. Otherwise, I'll assume that it's clear. And so I guess okay, so we have just finished in time, so it's 7:55 right now, and these are the questions which I had in mind for today. So Rasika, do you have any questions, any comments, or any queries, any closing words which you would like to say since this is our last session? this is our last problem solving session, not the. So we'll be having one more summary session tomorrow, but we won't be solving any problems in that. We'll just be discussing the concepts which have been done in all the lectures. Okay, thank you, Rasika, and thanks for attending the sessions. So I guess this is it, guys. So yeah, thanks for attending this session. So this wraps up our problem solving sessions for this semester for the competitive programming course. And so even though this was the last problem solving session, just to remind you guys again, we'll be having a summary session tomorrow, Wednesday, 17th April, from 5 to 6 p.m. In that session, I'll be covering like all the topics which we have done till now in the course, and we'll be sort of presenting a summary of everything. So we won't be solving any problems, but we'll just be doing the summary of the techniques which have been covered in these lectures. Okay, so I hope everyone enjoyed these sessions and hopefully they were useful to others also besides Rasika. And yeah, thanks for attending, guys. So we'll see you guys. We'll hopefully see you guys tomorrow in the summary session. So till then, I
Yeah.
guess we'll close the session and yeah, bye bye. Thanks for attending, Rasika.